Mass on a spring is a classic problem in mechanics. This is a real basic model that we're going to discuss. Not any actual new mathematics, we're going to discuss the differential equations with constant coefficients that we've already been doing and try and discuss qualitatively what kind of solutions can we get from that and how does that apply in some applications. Well, here's the mass on the spring problem. Suppose I have a mass M and it's attached to an ideal spring. By that I mean a spring with this force law. F equals minus a positive constant times u, the displacement of the mass. Well, I'll make the u-axis downward here, and if the mass is at position u from its equilibrium position where you could just hang the mass, let it go, and it would stay there, then the force exerted by the spring is minus some constant times u, called the Hooke's law constant of the spring. It depends on what the spring is made of and how thick it is, all that sort of stuff. But to a good approximation, springs behave like this. And you can pull it down u units and the force will be minus some constant times u. The minus here is to make it a restoring force, right? So it's at positive position u, the restoring force in this direction is negative, and if it's up here, if I compress the spring, then the force will become positive, pointing downward, trying to restore it towards zero. Alright, so that's what we call Hooke's law, actually, is the force is proportional to the displacement with a negative constant. And the mass is treated as a point object. It's got some fixed point position u along the u-axis. And we might also have some damping going on. We'll say, suppose the damping is proportional to velocity. This is what's often useful in applications, with some damping coefficient c, so that the force of damping is minus c times du dt opposes the velocity. If you're moving with a positive velocity, u pointing downwards, it's in that direction downwards, then the force opposes the direction of velocity and pushes you upwards. If you're moving upwards, then it pushes you downwards, is what that says. Finally, we might have some sort of driving force. It depends only on time. We've got a little motor attached, or we've got a little rocket booster on it or something. We can have a driving force. Then the total force on the spring, on the mass, is by Newton's law, mass times acceleration, right? Second derivative of position is acceleration. That has to be equal to the sum of all the forces applied. The damping force minus c du dt, the spring force minus ku, and any forcing function I call f drive here of t. Add these two over to the other side. You can rearrange the terms and say, well, that's md squared u dt squared plus c du dt plus ku equals the driving force, a function of time only. And you recognize immediately this is a second order linear differential equation with constant coefficients m, c, and k. And in fact, these are all positive constants by the physics of the situation. Makes it a little more restrictive. Equal to some force of t only. This makes it a non-homogeneous problem if a driving force is attached, or a homogeneous problem if there is no driving function. For this section, rather than doing too much, we're just going to consider the case where there's no driving force attached and this side is zero. It's a homogeneous linear differential equation of second order with constant coefficients, just what we've been doing. We know how to solve these. Today we want to see what the characteristics are. What do the solutions look like? How do they behave? So this is the classic mass on a spring problem, and we'll talk about the non-homogeneous case later, actually. And I'll just mention that actually there's an equivalent problem in electronics engineering, and actually in other fields too, but this is a famous one that we do. Suppose there's a circuit here. There's a wire running around, and there's three components along it. There's an inductor, L, a resistor, R, and a capacitor, C. The inductor is modeled by a coil of wire. I used to build these actually in junior high school. We still had shop class back then. Got to make one of these. But you make a coil of wire and run a current through it, and actually develops a magnetic field. And across this inductor, there's a voltage drop. So you can have some voltage attached here too, besides the three components. And there's a switch you can close at some time, maybe t equals 0 to get everything started. The resistance is modeled by a long piece of wire, right? Wires build up a little heat and you lose a little bit of your current. So that's the symbol for the resistor. And then two parallel plates symbolize a capacitor where charges plus and minus build up on both sides. And all three of those components have a voltage drop going across them, across the inductor. It has some constant L called its inductance. And if that inductance is L henries, then the voltage drop is L times di dt, where I is the current running through the circuit. By the way, I should mention that if Q is the charge on the capacitor, then the current running through there is the derivative of the charge. So the current running through the wire is dq dt. And then the voltage drop across the inductor is L, some constant that depends on the properties of the inductor, how many wires, what kind of wire, how many times you wound around, etc. Is L times di dt. Actually, in modern circuits, those things are microscopic, so, well, I don't know how small, but very small. Then this is L times d squared q dt squared. It's actually L times the second derivative of the charge on the capacitor. Across a resistor, the voltage drop is some constant R, the resistance, in ohms, times I, the current flowing through, and across the capacitor there's a voltage drop of 1 over C, where C is a number called the capacitance, multiplying Q, the charge of the capacitor. Now, Kirchhoff's law says that the voltage drop across, around a closed loop is 0, or if you have an impressed voltage, it's equal to the total voltage impressed. So, what we have is the sum of three voltage drops across the inductor, across the resistor, across the capacitor has to add up to the voltage impressed, which for today will be 0. We'll get a homogeneous equation. And you look at that for a second, and you realize, well, also, let's say often this voltage impressed might be sinusoidal, right? It's alternating current or something you're trying to push through there. And so the voltage will be sinusoidal. Then this is the same problem we had before, right? It's just with different letters. M, C, and K in the first problem equals some driving force over here. And here's the general charge on the capacitor problem, where I replace di dt with d squared q dt squared, since I is dq dt. And you get a second order differential equation with constant coefficients. Let's consider the homogeneous problem today when there's no impressed voltage. Here's the first case. Suppose there's no damping for the mass on the spring, or equivalently no resistor in the LRC circuit, we call it. It's just become an LC circuit, no resistor in it. Then you get this differential equation. How does the solution behave if you have a mass on a spring and no damping? Well, we just did that. Here's m d squared dt squared plus ku equals 0, the equation for the motion of the mass, its position u, given as a function of time t. The characteristic equation for this homogeneous second order equation with constant coefficients is mr squared plus k equals 0, right? Replace u with 1 and second derivative with r squared. And so we subtract k and divide by m, we find that r squared is minus k over m. And so r1 and r2 must be plus or minus the square root of that, which is 0 plus or minus square root k over mi. Pure imaginary solutions. Remember what happens when you get pure imaginary solutions? Something nice happens. For complex conjugates, you get e to the alpha t cosine beta t, we said, where these are alpha plus or minus I beta, are the complex conjugate solutions of the characteristic equation. And when, in the pure imaginary case, when alpha is 0, you get e to the 0t cosine beta t, we called it. E to the 0t sine beta t are two independent solutions. And so for a pure imaginary case, the exponential part falls out and you usually get cosine and sine for two independent solutions. The general solution of the mass of the spring is therefore C1 cosine square root of k over mt plus C2 sine square root of k over mt. That's how the motion of the mass goes, where C1 and C2 are arbitrary constants to be determined by initial conditions. All right. In here I used omega equals k over m, and this is what we get. And the result is C1 cosine omega t plus C2 sine omega t. You might like this letter because it represents square root k over m, but omega is commonly used for angular frequency. So what's happening here is the mass is actually oscillating with angular frequency omega equals square root k over m. This is the related to the actual frequency. The frequency is the angular frequency divided by 2 pi. Now here's an example. Suppose I have a mass that's 1 kilogram. And I've got a spring that's attached to it, it's hanging from the spring. And the spring has Hooke's law constant 4.0 newtons per meter. And if I extend that spring 8 centimeters below its hanging equilibrium, where it would just like to sit there and rest, and it's released, it's pushed upwards initially at 12 centimeters per second, find the motion of the mass of the spring for t greater than or equal to 0. It just goes up and down is the idea. Well, it's got this differential equation. 1 times d squared dt squared, because the mass is 1, plus k is 4 times u equals 0. And u of 0 equals 0.08. This is because I extended it 8 centimeters, but I'm doing this in meters. Right? So 8 centimeters is 0.08 meters. And then the initial velocity is 12 centimeters per second, so it's 0.12, and negative since I pushed it upwards against the direction of u. So there's my initial conditions, and what happens in practice is, we recall, is that a second order equation tends to take 2 initial conditions to determine a unique solution. So this will get the general solution that we saw before. These 2 will determine the constants C1 and C2 in the general solution to get a unique solution. So from a characteristic equation, r squared plus 4 equals 0 for this equation, we get r equals plus or minus 2i, and the general solution is C1 cosine 2t plus C2 sine 2t, right? The real part is 0, so it's e to the 0t cosine, e to the 0t sine, and e to the 0t is just 1. So we get this oscillating solution. Now, once we write down this general solution of the differential equation, we apply that u of 0 equals 0.08. Well, you plug in 0 here, and the sine of 0 is 0, so this falls out, and you get cosine of 0 is 1. You get C1 times 1 equals u is 0.08, evidently, right? You get C1 equals 0.08. Similarly, then you take the derivative of this, and the derivative is, you put in C1 equals 0.08, and you get minus 0.08 times 2 sine 2t, is the derivative of cosine 2t, and plus C2 times the derivative of sine 2t is 2 cosine 2t. Well, now you plug in an initial condition that u prime of 0, and this should be a 0 here, equals minus 0.12, and you get minus 0.12 equals minus 0.12 equals minus 0.08 times sine of 0, which is 0, plus 2c2 cosine 0, which is 1. So it gets 2c2 equals minus 0.12, and consequently c2 is minus 0.06. Now I put those constants in, and I have the exact motion of the spring. It's 0.08 cosine 2t minus 0.06 sine 2t. Alright, so there's the motion of the mass on the spring. This motion is actually quite significant. It's not some jumble. Maybe you remember from trigonometry the sum of angles formula. When you have sines and cosines of the same angular frequency, in this case 2, they sum to make another sine wave of the same frequency. That just kind of surprises me still to think about that. Why would you, anytime you have two sine functions, sine or cosine, sine waves, of the same angular frequency, you add them, they add up to a single sine function. You'd think they'd make a jumble maybe, but no, they make a single wave. And you prove it with the sum and difference of angles formula from trigonometry. So the point is that any sum like this can be written as an amplitude times a single sine function with a phase shift. A phase shift due to some number of phi here, which the phase shift is minus phi over omega, actually. So here's the theorem from trigonometry, sum of same frequency sine waves. If you take a constant times cosine omega t and a constant times sine omega t with the same omega, it's equal to a constant times sine of the same omega t plus some other constant. And it's always true for some constants a and phi. It comes up from this. In this expression, you let a be root sum square of c1 and c2. Let c1 hat denote c1 over the square root and c2 hat be c2 over the square root. Then you can rewrite u equals this. Let's see. You can write u equals c1 cosine plus c2 sine as u equals a, right, times all this stuff, because a times c1 hat, if you multiply it out, is c1, and a times c2 hat is c2. So this says c1 cosine plus c2 sine, just like you had before. All you did was change the names of your constants. Now here's a picture up here we can use. Since c1 hat squared plus c2 hat squared equals 1, we know it is, right? This squared plus this squared gives c1 squared plus c2 squared over the same is 1. You just take this squared plus this squared, see it's equal to 1. C1 hat, C2 hat, C1 hat is actually a point on the unit circle. So you can go around and sketch it over here. C2 hat, C1 hat. And therefore, C2 hat, remember the unit circle, any point on the unit circle is a cosine of the angle here to the point and the sine of the angle to the point respectively. So it must be that C2 hat is cosine of that angle and C1 hat is sine of that angle. And where the angle is called the phase angle. And we can pick angle between 0 and 2 pi or minus pi and pi. Those are both conventions people use. But the point is, this last expression we had, C1 hat cosine plus C2 hat sine, since C1 hat and C2 hat are on the unit circle, they can be interpreted as a sine and a cosine, respectively, right? Since they're on the unit circle, they're a sine and cosine of some angle. And that means we can rewrite our general solution in this form for some angle phi, which is just a constant. But wait a minute, now sine, cosine plus cosine sine, the sum of angle formulas says that sine of, sine of alpha plus beta is sine cosine plus cosine sine. So this can be rewritten as u equals a times sine of omega t plus phi, right? Sine, cosine plus cosine sine is the sine of the sum of these two angles, phi and omega t. So what we've done is seen that the mass on the spring oscillates as a single sine wave at some amplitude, which is the root sum square of c1 and c2 if you look above. Sine of square root k over m was omega t, plus some phase angle phi, which is the, you can figure it out as an arc tangent. So it looks like this. It's the mass goes up and down and up and down, and as a function of time, its displacement u is up and down like this. I have a display here. Let's see if I can get it up still. This one. So here's the, oops, this is the wrong one. Let's see. Should have two of these. this up and it went away somewhere. There we go. This is the one. So this is what it does is the mass goes up and down. We plot its displacement here, and it moves with this simple harmonic motion, we call it. It's a sine wave. All right, and phi can be calculated as for a point x, y in the unit circle as arctangent y over x, or that plus pi, depending on what your quadrant is in. There's this a-tan2 function available on a lot of programming languages that can calculate it, which one between minus pi and pi using this a-tan2 function, or you can calculate it by hand, saying that the angle is always the arctangent y over x, or that plus pi, plus or minus pi, depending on what quadrant you're in. So you can figure it out. Here's what we can do, for instance, on the last example. The solution was this, 0.08 cosine minus 0.06 sine. I wonder if I can write that as a single sine wave. So I do what I did before. I said the amplitude is the root sum squared of the coefficients. Square root of 0.08 squared plus 0.06 squared is 0.1. So it's 10 centimeters is the amplitude of the motion. The period of a sine wave that has angular frequency 2, you recall, is 2 pi over the angular frequency. Is 2 pi over 2 is pi, so it oscillates every pi units of time. And the angle is the arctangent of C2 over C1. Or the C1 over C2, I've forgotten now. But it's arctangent of, C1 over C2. And the reason being that this is in quadrant 4. In quadrant 4, right, when if you plot C2 and C1, in quadrant 4 you don't add the pi. And it shows you that the phase shift is about is minus 1.1 because phi comes out to be 2.2. So here's the solution written in the other form, 0.1 sine of 2t plus 2.2 omega t plus phi. And now you have the evident simple harmonic motion from the mass of the spring. Here's another one. This is kind of a trick. If you work in English units instead of the international units, you use pounds for measuring mass, but pounds isn't actually a mass. Maybe I shouldn't write mass here. Pounds is a force. An 8-pound object, I should say, is hung from a spring. Mass is actually measured in slugs. You take the pounds and you divide by the acceleration of gravity, 32 feet per second, and you get actually the mass is 1/2 slug. So here's a 1/2 slug mass on the end of a spring, and gravity is 32 feet per second squared near the surface of the Earth. So suppose I have this mass in a spring, and suppose the spring, if it weren't stretched, would hang a certain length, and the mass, when it hangs on there, pulls it down 6 inches from its natural length. We can figure out what the spring constant is from that, right? Now suppose that it's released 1 foot below its equilibrium position, so u of 0 equals 1, and the initial velocity u du dt equals 8 square root 3, downward since velocity is positive. Find the position for all time and eternity in this model. Well, pounds is a force, so the object exerts a 16-pound force, and you get m equals 1/2 slug from 16 pounds of force. The spring extends at 6 inches, that's 1/2 foot. We have to put everything in terms of feet, just like last time we had to use all meters. So minus the spring force is equal, k times 1/2, k times the displacement, that's ku, and you observe that K must, if the spring force is 16, and K, and that's equal to K times a half, you get K is equal to 32 pounds per foot. All right, the model is therefore mass times d squared u dt squared plus K times u equals 0, where K is 32 and mass is 1/2. We figured out by attaching the spring and hanging it and see what happened. Now the initial position was 1 foot down, the initial velocity was 8 square root 3 feet per second downward. So we can solve this thing. The characteristic equation is 1/2 r squared plus 32 equals 0. So we get r squared equals minus 64, and r1 and r2 are plus or minus 8i, right? Square root of 64 times i. It follows that the general solution is an arbitrary constant. I call it alpha 1 and alpha 2 instead of c1 and c2 here for some reason. But c1 cosine at plus c2 sine at is the general solution of the differential equation for the motion. Initial conditions will determine the specific motion, right? So if I put u of 0 equals 1, u prime equals 8 square root 3. First I put in 0 for t and 1 for u, and I get this equation. Then I put in 8 square root 3 for u prime, and here's the derivative of u at is, right, minus 8 alpha 1 sine plus 8 alpha 2 cosine. If you plug in 0, this is what you get. So the derivative plug in 0 on the right hand side. This is, well, cosine of 0 is 1, sine of 0 is 0. So it reduces to this system, alpha 1 equals 1, 8 alpha 2 equals 8 square root 3, from which you deduce the constants alpha 1 and alpha 2, or 1 and square root 3. And the motion specifically is cosine at plus square root 3 sine at. Putting these two constants back into the general solution. I put them in here, and you get this. This is nice, it is the exact solution, but it's nicer to see it in that form that makes the sinusoidal motion evident, right? We compute the amplitude as the root sum square of the coefficients, 1 squared plus square root 3 squared is 2, and that the angle is the arc tangent of this one over this one. And again, since this point, with this, the y coordinate, and this the x coordinate, is in quadrant 1, so we don't want to add pi to compute the arc tangent. The arc tangent of 1 over square root 3 is pi over 6, and so with phi equals pi over 6, the phase shift is minus pi over 6 over 8, which comes back here somewhere. And you have this sine wave, simple harmonic motion, for the motion of the mass. Its displacement on this axis and time t on this axis. There it is. Now, this makes an interesting point. It does not matter how you start at what speed, what position. It always oscillates with this natural angular frequency, 8 in this case, or 2 in the other case. Every spring has a natural frequency. If you start in motion, it will oscillate with the same frequency because it just depends on the spring constant and the mass. And it's always square root k over m is the angular frequency. So we can calculate the angular frequency of these as square root k over m for any mass of a spring problem and see exactly how fast it will oscillate. And then the actual frequency. All right, here's just kind of a fun picture graph. It shows that actually bridges can behave like this. This shows if you apply a force, here's the extension of it, and you can apply these things to bridges and so forth. Well, let's find the charge on the capacitor now of an LC circuit. That behaves like a mass on a spring with no resistance, because if an LC circuit, you can take the resistor out, just include the inductor and the capacitor. Here's a closed circuit, so the charge starts flowing around the thing, and the corresponding electronic equation with no impressed voltage, so you put 0 on the right, and no resistance, so you get out the dq/dt term. That equation we wrote before looks like this, and it has some initial conditions. So there's an LC circuit. What happens to this? You write the characteristic equation, LR squared plus 1 over C equals 0 is the characteristic equation. And you divide through by L and get this, R squared plus 1 over LC equals 0. You get R equals plus or minus 1 over square root of LCI, and therefore you get simple harmonic motion again with this time angular frequency 1 over square root LC. And so this is the general solution to the LC circuit. You get it oscillating back and forth, and you can, generate an antenna sending out a frequency and catch an antenna out to here, so the electrons are forced to switch up and down by the circuit. You can make a signal at a particular frequency kind of thing. All right. So there's the LC circuit. It has a natural angular frequency of 1 over square root LC. If you take the interest, there's some videos you can see about mass spring motion more generally, and you talk about things like, well, you can have transverse waves like this that oscillate perpendicular to the direction the spring is, or you can have longitudinal waves where you push a slinky here and make little bumps in it where it's closer, more compacted, and other where it's more extended. And so you can have longitudinal waves and transverse waves and model both of these with these kinds of equations. Well, one more thing now, suppose we want to add a resistance in here to the circuit, or some sort of damping force to the mass of the spring. Now we have an additional term we said before, and we'll still say suppose there's no forcing term. So we get a homogeneous linear equation with constant coefficients. What if this middle term is now included? The simple harmonic goes away, simple harmonic motion, and we actually get 3 different cases. If you write the characteristic equation for this one, mr squared plus cr plus k equals 0, it's a quadratic equation. You can always find the solution to that with the quadratic formula. And what happens in the quadratic formula, the discriminant, for ar squared plus br plus c equals 0 is b squared minus 4ac. For this one with the different letters, the discriminant is c squared minus 4mk. And if that's positive, you get 2 real distinct solutions, R1 and R2, and the solution is C1 e to the R1t plus C2 e to the R2t. Remember, if you have 2 distinct solutions for A u double prime plus B u prime plus cu equals 0, you get exactly this when you have 2 distinct real numbers. All we've done is change the letters from ABC to MCK, and it's the same solution you had before. If c squared minus 4mk equals 0, if the discriminant is 0, then there's 2 real equal solutions, and we have this solution, right? You wanted e to the R1t was one solution, t e to the R1t was an independent solution. When you add them together, you get this general solution. And then the other possibility is you get complex conjugate solutions from the quadratic formula. If c squared minus 4ak, the discriminant for this one is negative, then R1 and R2 are alpha plus or minus I beta for some numbers, some real numbers alpha and beta. And you get independent solutions of the form e to the alpha t sine and e to the alpha t cosine. And when you combine them together, what you can get, now let me just put the derivation of this. What is here? You get something of this form. And so this is, I think it's down here. Maybe not. But when you have a constant, I'll write it here. What you get is a general solution that looks like this. U equals C1 e to the alpha t cosine beta t plus C2 e to the alpha t sine beta t is the general solution for the damped mass on the spring, or the LRC circuit. What you do now is you factor out e to the alpha t times C1 cosine beta t plus C2 sine beta t, and recognize that this is what we had from the harmonic oscillator. This can be rewritten by trigonometry as a sine beta t plus phi, or maybe you want to call this omega at this point instead of beta. all times e to the alpha t. And what you get then always out of this damped oscillator is an exponential times a sine wave, and you get a particular behavior. The exponential function looks like this, its negative looks like this, because it turns out that alpha is always negative. Because the three constants, m, c, and k, are all positive, it turns out alpha always has to be negative. You just kind of have to look at it at the quadratic formula to see that. But you get a decaying exponential, e to the alpha t, alpha being negative, and multiplied by a sine wave of amplitude a. Sine goes between plus and minus 1, so if this is a e to the alpha t, and this is a minus a e to the alpha t, alpha negative, you get something that oscillates between plus and minus 1, multiplying them. This is what the solution looks like. It damps out like that. So we have three different cases, and I'll show you the picture now. It's kind of a long section, isn't it, even though we're only doing the homogeneous case. All right. Here's what we have, and I can show you the picture for this one now. Let's see. Oops, that's the wrong one. Let's try this again. Here's a damped mass on a spring. So you oscillate between these two decaying exponential functions. This is modeled by a dashpot damper, they sometimes call it, when it's damping proportional velocity. A big plate here moving slowly through a fluid might exert friction proportional to velocity. And real life friction is proportional to velocity squared for moving through the air for moderate sized objects. So I wrote it this way. Now, here's some examples. Suppose I have d squared u dt squared plus 5 du dt plus 4u equals 0. This could be for a mass 1, damping coefficient 5, and spring constant 4. It has two solutions to the characteristic equation. R1, R2 is minus 4, minus 1, and so the general solution is C1 e to the minus 4t plus C2 e to the minus t. The second case, suppose I put a little less damping, I change the damping coefficient to 4. Now the characteristic equation R squared plus 4 equals 0 has equal real solutions. And this solution, e to the minus 2t times C1 plus t e to the minus 2t times C2. The other case, if I put a little less damping, then it does like the picture you saw, and the damping coefficient is 2, you get complex solutions, minus 1 plus or minus square root 3i, and this general solution, a constant times e to the minus t, minus 1 times t comes from here, times sine square root 3 comes from here, t, plus phi, for some arbitrary constants a and phi, to exhibit that it's an exponential decaying times a sine function. So here's the picture. The one decays like this, the second decays like this, and the third decays like this. Because this one damps as rapidly as possible out of the 3, this is when the R1 equals R2, we call that situation critical damping. The one where we had so much damping that it went slowly without just decaying exponential, we call overdamped, and this one that oscillates up and down, we say is underdamped. And so you can restore the mass to towards its equilibrium position asymptotically as quickly as possible by choosing critical damping. This also applies to the LRC circuit because it's exactly the same equation, just derived from a different source. It's the charge on the capacitor. Try the problems and see if you can do those.